Okay, this is part 3 in the arrangement of electron series. We're going to talk about the Bohr model and quantum numbers. So let's start off with our Bohr model discussion. Niels Bohr came up with his model of the atom after he discovered the discontinuous hydrogen line spectra, and determined that the different peaks or the different lines on that line spectra corresponded to energy levels. And so this is the model that he came up with. He included Rutherford's idea that the nucleus was very small and in the center, and it was positively charged. And up until this point, nobody had said anything about the electrons, and then he came along and said, you know what? There are energy levels, he called them, that surround the nucleus, and the electrons have to stay within these energy levels. Okay? So, let's see if we can do a Bohr model of the atom example. Okay, so here are 3 example problems. The main idea is that these outer rings, we call those energy levels or orbitals. The inside is the nucleus, which contains the protons and neutrons, and the electrons have to stay on these outside rings. Okay? So let's see if we can figure out hydrogen first. That one's the simplest, so we're going to do that one first. Okay? Let's look at the periodic table. Alright, so hydrogen. Hydrogen has a molar mass of 1, essentially, okay, and it's got an atomic number of 1. And we've practiced this before. We said that the molar mass was equal to the protons plus the neutrons, okay, and that the atomic number was equal to, I'm just going to have to do, like make up my own thing here. The atomic number is equal to the number of protons, okay? So, if I want to know what the number of neutrons are in a hydrogen atom, then I'm going to have to take the molar mass and subtract the atomic number. That means that the protons will cancel out, and I'll be left with neutrons. So that would be 1 minus 1, so 0. Okay? So we know that inside of the nucleus here, we've got 1 proton and 0 neutrons. Okay, well now how many electrons does it have? Okay, the charge of an atom or of a compound has to be neutral. So if there's 1 proton which has 1 positive charge, then there has to be 1 electron so that it'll have 1 negative charge and it'll balance out. So there is 1 electron there on that energy level. Okay? Alright, let's do sodium next. Okay, so here is sodium, and it's got 22.9, that's about 23 for the molar mass, and 11 for the atomic number. So we're going to say 23 minus 11. Alright, so that gives us 12 neutrons. Okay, so 11 was the atomic number, so that's going to be the number of protons. And it's also going to be the number of electrons because the charge has to balance out. So, and then we've got 12 neutrons. Okay? Okay, so let's start placing our electrons. Now we do have to follow the idea that each energy level can only hold so many electrons. Okay? So, for example, the first energy level can only hold 2 electrons. The second energy level can hold 8. So, and when you place these electrons, you need to, or what I do is I place them like on the 4 sides here, and then you go back and pair them up. You do not start out by pairing up the electrons. They need to be placed individually first. Okay, so right now we've got 8, 9, 10. And so we've only got 1 more electron that can be placed, and so we'll put that one on the third energy level out here. Okay, so that would be the correct Bohr model for sodium. Alright. Now, I bet you're wondering how I knew how many electrons can go into each energy level. We're going to actually learn that when we get into the quantum numbers section. I'll tell you real quick what the rule is, and then we'll come back to it later on. We're going to say that each energy level is a number. So like that's the first energy level, that's the second energy level, that's the third energy level. Okay? So here's the, and we're going to say that any given energy level can be named N. Okay? And that we'll come back to this N here in a little while. So the rule is 2 times N squared. That tells you how many electrons can go in each energy level. Okay? So for example, if N equals 1 because we're in the first energy level, then you would put a 1 up here. So you would have 2 times 1 squared. And 1 squared is 1 times 2 is 2. And so that's why there's only 2 electrons allowed here. Okay, if you said that N equals 2, then you would have 2 times 2 squared. And 2 squared is 4, and 4 times 2 is 8. So the second energy level can have 8 electrons, and so on and so forth. So the third energy level is going to have 18, and we can just keep going from there. So this is a pretty handy rule to keep in mind if you want to know how many maximum number of electrons can fit inside of an energy level. That's the rule. I will show you and prove that to you with quantum numbers later on in this video. Okay, so potassium is the last one, so let's take a look at potassium, and we see that we've got 39 approximately as our molar mass, and we've got 19 as the atomic number. You'll notice, I hope, in the previous examples that I have rounded these molar masses. You cannot have a decimal point number of neutrons. You must round to the nearest whole number. So we've got 39 and we've got 19. Okay, so we're going to take 39 and subtract 19 from it. And so we get 20 neutrons, and then this was our number of protons in the nucleus, and it's also the number of electrons in our energy levels. Okay, so we place 2 electrons in the first energy level. Then we're going to go in and place our 8 electrons in the second energy level. And remember, you only pair them up after the first 4 are already there. So right now we have 10 electrons on the atom, and we need 9 more. Okay, so how many electrons can the third energy level hold? Let's check our rule out here. Okay, so 3 squared is 9, and 9 times 2 is 18. So we can definitely fit these in here. Okay, so let's see, we've got 1, 2, 3, 4, 5. That was supposed to be on that line. 6, 7, 8, and then we'll have one more right here, 9. Okay. And you'll notice that I just kind of moved halfway in between my top and my left-hand side. I split the difference here, and that's where you would put your next set here, 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 and here to go ahead and get up to 18 before moving on to the next largest ring. Okay? Alright, so hopefully that makes sense to you. That's not a big deal. Being able to describe how many protons and neutrons are in there. Okay, so there are 19 protons and there are 20 neutrons, and then we've got our 19 electrons that are orbiting the nucleus. Okay. So anyways, if I put on a quiz or a test something about you filling in a Bohr model or draw the Bohr model for such and such element, that's how you do it. Okay. The electron, when it's in each of those orbitals, has different amounts of energy or quantum. Okay. And if it's closer to the nucleus, or the whatever energy level is closest to the nucleus, that's the ground state that we talked about in the last video, and that is the lowest energy state that the electron can be in. And when the electron jumps from one energy level to the next, it cannot move in the space between. Okay, and we saw that in the clip from Cosmos in the last video. Okay, so I don't know, let's say that this was carbon. Okay, so if we look at carbon here, we can see it's got 6 as the atomic number and 12 as the molar mass. So we'll take our 12 minus 6, and that's going to give us 6 for the neutrons, and this represents the protons and the number of electrons that we're going to have. So inside the nucleus, we'll say there are 6 neutrons and there are 6 protons. Okay, and then we'll put on our electrons. So there's 1, 2, 3, 4, 5, 6. Okay, so the electrons here in the lowest energy level, if they were going to jump into a higher energy level, then that's where they would receive that photon of light that would give them extra energy, and it would jump up here. And the amount of energy that that photon has to give it must be exactly equal to the energy difference between this energy level and this energy level. If it's even a little bit less, then the electron will not move. If it's too much, the electron will not move. It has to be exactly the same amount of energy difference that's between these two orbitals, and then the electron will jump up to a higher energy level. And then it will fall back down and it will release another photon of light that's equivalent to that same amount of energy. Now the cool thing is when that electron is moving from this orbital to this orbital, it does not pass in between. It just stops existing here and reappears here. Okay? And you saw that in that previous video, and that is called quantum tunneling. Okay? When an electron vanishes and reappears, that's called quantum tunneling. That's actually how the fusion reaction in the core of the sun works. Without quantum tunneling, our sun would not be able to do that fusion reaction where two hydrogen nuclei fuse together to become a helium, and therefore there would be no life on this planet, because we can't live without the sun. Well, as you can imagine, after we figured out where the electrons are, then we started trying to prove that, and we wanted to prove it by actually seeing them be there, rather than just theoretically saying this is the evidence we have to support it. We want to actually go see it. So we started trying to take a look at where an electron is, and we wanted to gather all this information about it. And when we tried, we were able to figure out where the electron was, its position, but we couldn't see how fast it was going. A lot of times you'll see them say momentum, but same kind of business there. So we couldn't know how fast it was going, or if we knew how fast it was going, we couldn't know where it was while it was moving that fast. A guy named Heisenberg was the one who tried to figure this out, and he realized it can't be done. So he came up with the Heisenberg uncertainty principle, which says that it is impossible to determine simultaneously both the position and velocity of an electron or any other subatomic particle. So even the particles that we play with today in the Large Hadron Collider or CERN in Switzerland, the neutrinos and the God particle, I'm sure you've heard of that, and all these other little subatomic particles, they follow this Heisenberg uncertainty principle. There actually has been recent work done, though, that has allowed us to sort of kind of know the position and speed at the same time. And some researchers have played around with some quantum mechanics and have figured out a way to sort of kind of get to know both of them indirectly, figure out one of them and know the other one. So we are advancing technologically speaking, and maybe the Heisenberg uncertainty principle is not going to be around for too much longer. Who knows? Then we came up with quantum theory. Okay, and the quantum theory is a set of mathematical equations that will describe the wave properties of electrons and other small particles. It helps to explain how an electron can behave, and also how a photon of light or any other small particle can behave both like a wave and a particle. There's that wave-particle duality we talked about earlier. Quantum numbers are the answers to the equations of quantum theory. When you solve the equations, the quantum equations or Schrodinger's equations, you get these 4 quantum numbers, and they will identify what atomic orbital an electron is in and all kinds of other properties of that electron while it's in that orbital. And so I tend to think of those 4 numbers here as an address for an electron. Let's watch a clip of Dr. Quantum as he explains a famous experiment called the double slit experiment and how subatomic particles can behave like waves and particles.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, 2 bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through 2 slits, we should get, like the marbles, 2 bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay, so hopefully you found that enjoyable and it helped you to understand a little bit more. One thing I did want to talk about is the fact that looking at the electron or any other subatomic particle collapses the wave function. When he talks about that, he's really talking about Schrodinger's equations and the wave equation that we dealt with in a couple of videos back. And why do you think it did that? Why would the electron stop behaving like a wave as soon as you started looking at it? Well, the answer to that is because something else happened. When you look at something, okay, in order for you to see it, that thing has to be illuminated, meaning light has to strike that object and bounce off the object and then be received by the retina of your eyeball in order for you to know that it's there. If I were to stick you in a perfectly dark room with zero light in front of it, and I was standing there in front of you holding an apple in my hand, and I asked you, how long do you think you'd have to sit here before you could see this apple? Some of you might say, oh, I'll be able to see it in 10 seconds. Another person might say, I'll be able to see it in 30 seconds. The actual answer is you will never be able to see the the apple. If there's no light in that room, you will never see anything in that room. You have to have light in order to see something. So when they tried looking at that electron, what they actually did is they shot photons at it. They illuminated, they looked at it with a camera or some other measuring device, and that device struck the electron. Let's say the electron is zipping by right here. They struck it with a photon, a packet of light. That knocked it off course. It's not going to behave like it was anymore because something interfered with it, and that's what collapsed the wave function. Okay, let's talk about the atomic structure and how the electrons fit into it, okay? Obviously, from the Bohr model of the atom, you might have realized or noticed that it looks very similar to our solar system, okay? The protons and the neutrons are in the nucleus in the center of the atom, and then the electrons orbit around the nucleus just like our planets orbit around the sun. Okay, we know that electrons are negatively charged. We know that protons are positively charged, and neutrons have no charge at all. Okay, they're neutral. And that these protons and electrons are attracted to each other from that electromagnetic force of attraction that we started the first video out with. Okay, so that's what this electrostatic attraction is. A lot of times scientists will split up electromagnetic into an electrostatic force and a magnetic force, but really they're both the same. Okay? And then just as the planets have different orbits, the electrons do too, and we've already talked about that, okay? Depending on what element they belong to, there may be more or less orbitals that they fill up, okay? We'll talk about Hund's rule in a little while. Okay, now we're going to really get into our discussion of quantum mechanics and Schrodinger's equations and quantum numbers. So this is where I really need you to focus in, okay? If you missed it in class, this is what you need to pay attention to right now, all right? Okay, so quantum levels are the same thing as saying shells. There's a whole bunch of different names for energy levels, okay? And these are just two more, okay? So each of the energy levels themselves, those rings, can be called quantum levels. Sometimes they're called shells. Sometimes they're called clouds. This is really the new terminology that we stick with. We do call them clouds because we understand that they aren't actual rings. Okay? Well, each one of those electron clouds or levels or whatever you want to call them is made up of what we call a subshell, or a different area of space that has a different shape, and we name those areas of space S, P, D, and F. Okay, and I'll talk about those a lot more in just a minute. The lowest energy level of an electron is going to have a spherical shape, and that is the S subshell. This S does not stand for spherical, but if it helps you remember it, by all means, please do that. In fact, I do that myself. The S subshell is going to be a spherical shape. Okay? There is only one S subshell per quantum level, and each S subshell is going to have a spherical orbital with room for 2 electrons in it, because remember, that very first energy level can always hold 2 electrons. Okay, the next higher energy levels can orbit once the S subshell is filled, and then we move on to the P subshell, which can hold up to 6 electrons each, and then we can go to the D and then to the F. Okay? Okay, so let's talk about the 4 quantum numbers. The first one is called the principal quantum number, and it is signified with the lowercase letter n. Remember, this is what I used earlier when we did the Bohr model of the atom, and I gave you that formula, 2 times n squared. The n that we're talking about is the principal quantum number. It is the period that an element is in, okay? So if we came through here on the periodic table and we numbered each period, remember the periods run side to side, you'll notice right here this says 57 through 70 and 89 through 102, which means that the lanthanides belong right up in here, and the actinides belong right here. Okay, so that means that this is row 6 and this is row 7 also, because it really fits right there in that space. Okay, alright, well, these purple numbers that I've just listed here, those are the principal quantum numbers. Okay, each of those is in. Okay, so if I was talking about lithium, lithium has a principal quantum number of 2. Sodium would have a principal quantum number of 3, and so on and so forth. So these can only be positive numbers, whole numbers. We don't have 1.5 row on the periodic table. Okay, the principal number tells you how far away from the nucleus you are. Remember our periodic trends. Okay, let's see. We know that as we increase our N value, we are moving away from the nucleus, and therefore the electron is being held on less and less tightly. Another periodic trend. Okay, so that's all of our principal quantum number information so far. Let's look at the angular momentum quantum number. It is symbolized by this kind of cursive-y looking lowercase l, and it is equal to n minus 1. So the principal quantum number minus 1. Alright? L indicates the 4 sublevels, S, P, D, and F. Okay, so L represents S, P, D, and F subshells. So here's kind of a table that helps us out here. I'm going to come in here and put what the principal number has to be in order for these L values to be true. Okay, so if n equals 1 and L is n minus 1, then 1 minus 1 is 0. Okay, so when n is equal to 1, then we can have an L value equal to 0. Okay, a 0 L value corresponds to the letter S subshell. Okay, so it's just two ways of saying the same piece of information. You can either say that it is the S subshell, or you can say that L equals 0, and that stands for S subshell. So those two things are the same, alright? And 1, L equals 1, corresponds to a P subshell. Okay, and L equals 2 corresponds to a D subshell. And L equals 3 corresponds to an F subshell. So those are just two different ways of saying the same piece of information. Okay, so the S subshell is spherical, and then it's going to have a maximum of 2 electrons in it. Remember, the 2 times n squared gives us this. Okay, same thing on this one. The P subshell is polar or dumbbell. I think they kind of look like teardrops that are connected to each other. Ooh, that bottom one's not good. And there are 3 p orbitals. Each of them can hold 2 electrons. So 2 times the 3 orbitals gives us 6 total electrons in a p orbital. The d orbital, there are 5 of them. 2 electrons in each of those 5 orbitals gives us 10 total electrons allowed in the d orbital. It looks like a clover leaf, and what they mean by that is something like this. Okay, so that's kind of the shape of the d orbital. And in the f orbital, there are 7 of them. Each can hold 2 electrons, and so 14 total electrons in the f orbital are allowed. That one has complex shapes. There's so many different ones, and they're way too difficult for me to draw, so I'm not going to try. Alright, each subshell is going to have a different shape, as you'll see in these pictures below that I'm going to show you, but I want you to think of these subshells, S, P, D, F, as like pockets in your pants, okay? Just because there's nothing in your pocket right now doesn't mean that your pocket is not there. So these subshells are always there, ready and waiting for an electron to jump in. They don't stop existing just because there's not an electron in it yet. Okay, so here's kind of some pictorial representations of these subshells. So here's the S subshell. It's not a circle, it's actually a sphere. So they really should have done that better, I think. See if I can go in and try and make that look more like a sphere for you guys. Okay, so best I can do. Alright, so inside of this spherical s orbital, there's allowed to be 2 electrons in there. and they can be anywhere in there. They don't have to be just on the outside. They can be anywhere in this spherical space. Okay, that's why we call it an electron cloud, because they can fill up anywhere in here. They don't just stay on the outside edge like that. Okay. And then we've got a p orbital, okay, and there are 3 p orbitals like that table said above. Okay, so we've got one p orbital here, another p orbital here, and a third p orbital here. Okay, and every p orbital can hold 2 electrons. So we've got 1, 2, 3, 4, 5, 6. All right. You don't lose this one. When you go up from the s orbital to the p orbital, they just kind of overlap each other, like this picture shows down here. So this is kind of replacing the Bohr model of the atom. If you'll notice, we've got 2 electrons in our first energy level, the s orbital, and then the second energy level, it's got 1, 2, 3, 4, 5, 6. And then here, these first 2 are 7 and 8. So the whole thing, this whole thing right here, would be the second ring on a Bohr model of the atom. The first ring would just be a sphere by itself. Okay, so the first energy level is just a sphere. The second energy level is a sphere plus the 3p orbitals all combined together. So that's where we get 8 and we get 2 on that one. Then we could move up to D and have this clover leaf, and that one would overlap on top of all of this. It just keeps getting bigger and bigger and bigger. Okay, so this slide here just kind of rehashes what I've already said. L can either be 0 or it can be positive integers of n minus 1. So here's kind of an example of that. If n were equal to 2, then 2 minus 1 is 1, so L would be 1 there. Okay. If n was equal to 1, 1 minus 1 is 0. And those add, we keep both of those, so we could be 0 and we could be 1. So if n equals 2, then L can be 0 and 1. Alright? It's 0 because the first energy level was 1, and 1 minus 1 is 0. And it's 1 here because the second energy level is 2, and 2 minus 1 is 1. So if n equals 2, L is both of those things. Okay? Alright, the third quantum number we're going to talk about is the magnetic quantum number, and it's symbolized by an M sub L, and it's that same cursive-y looking L. Okay? And this one tells you the orientation or the position around the nucleus of the orbital. Okay, the values are going to be anywhere between negative L and positive L. Okay, the s orbital can only have one possible m sub L value. There needs to be a little sub L. And that's because it's a sphere, so it doesn't matter how you rotate a sphere, it looks the same no matter which way you look at it. Okay, so let's do a little practice thing here. If n is equal to 2, then L can be 0 and it can be 1. Remember that these numbers correspond to letters, so 0 was for S and 1 was for P. ML, okay, if we're doing ML and we're using 0 as our L value, the value can be anywhere between negative L and positive L. So that means anywhere from negative 0 to positive 0, which is just 0. Okay? So that's what they're saying right here. An s orbital can only have an m sub L value equal to 0, and that's this right here. Okay? And no matter which way you rotate a sphere, it looks the same. Now let's do the p orbital. Okay? Anything from negative L to positive L. So it is all positive whole numbers between negative L and positive L. So that would be negative 1, because L equals 1, so we're going to negative L, negative 1, and then 0, and then positive 1. So those are the m sub L values if L is equal to 1. Notice there's 3 of them here. That corresponds to these 3 pictures. Okay, the first one, -1, is when the dumbbell shape is on the x-axis. The middle one, 0, is when the dumbbell shape is on the y-axis. And the last one, +1, is when the dumbbell shape is on the z-axis. And that means that it is coming out of the page and into the page. So it's coming out towards you like 3D. If you're at the movie theater and you're looking at the screen, it's coming out towards you, or it's moving into the screen, so it's deeper. Okay, so these 3 numbers correspond to these 3 shapes, so we call it px, py, and pz. Alright, so right down here we would have px, we would have py, and we would have pz. Okay? Here are all of the orbital shapes that we can come up with. We have an s orbital here, so this is our sphere. Here we have a p orbital, and it's got 3 orbitals in it. Okay, so this is the first shell, this is the second shell, and the second shell contains everything that came before it. Okay, and that's true for all of these things. It contains all of the stuff that came before it. So the second shell is going to have an s orbital and 3 p orbitals. The third shell is going to have 5 d orbitals and 3 p orbitals and an s orbital. Okay. Now here are those d orbitals. This is that clover leaf. Okay. So here you'll notice that they're all kind of on this x-axis. Then here it's been flipped up, so they're on the y. Then here it kind of, these middle ones turned into a ring, and we've got like a polar shape through the middle. Then here this one has been mirrored over here, and here this one has been mirrored. So there's several shapes there. And then here is the f orbitals, and those were what we called complex, because you'll notice, look at how many different shapes we have here. Way too many to draw, and too difficult to draw. Okay, the last quantum number, the fourth one, is called the spin quantum number, and it's symbolized m sub s. Okay, there are only 2 possible values. You can have a +1/2, or you can have a -1/2. And that indicates in which direction the electron itself is spinning in the orbital. If you have a +1/2, then the electron is going to have a clockwise spin, and so you'll see me do this kind of an arrow here. Or if it's a -1/2, then you would have a counterclockwise spin, and you'll see me do this. Okay, I'm going to make those bigger because those don't look very good. So clockwise spin and counterclockwise spin. Okay. Again, a single orbital can only hold 2 electrons. I don't care what orbital it is. A single orbital can only have 2 electrons in it, and those 2 electrons must have opposite spins. One has to go clockwise and one has to go counterclockwise. The reason for that is because electrons are both negatively charged, and so because of the electromagnetic force, they actually should repel. I mean, like charges, the same kind of charge doesn't want to be near another same kind of charge. They want to repel away from each other. So the only reason that the electrons actually stay in their orbitals with each other and don't go flying off into space is because they generate a magnetic field. When one of them moves clockwise and the other one moves counterclockwise, this magnetic field is generated, and that attracts them both to each other. Okay, so let's do another one. Let's say n equals 3. Alright, that means that L can be all of the values from n minus 1 and onward. So 3 minus 1 is 2, and we can have 2 minus 1 is 1, and 1 minus 1 is 0. Okay, so those are all of the possible L values when we have n equals 3. And then m sub L. Okay, so if we do L equals to 2, then that's going to be -2, -1, 0, +1, +2. Okay, and remember our L values stand for our subshells. So this is S, this is P, this is D. Okay, so I'm going to kind of put a little separator line here, and now we'll do L equals 1. Okay, so we would have -1, 0, and 1. And then, let me put another separator. Let's do the 0 here for the S subshell. Well, from -0 to +0 is just going to be 0. Okay, so we're saying we've got 1 orbital here, we've got 3 orbitals here, and we've got 5 orbitals here. And so we're actually in this situation right here where n is equal to 3, and so it's going to contain these 5 orbitals, it's going to contain these 3 p orbitals, and it's going to contain this s orbital. That's just for the third energy level. There's also a second energy level that's going to contain both of those, and there's a first energy level that's going to contain just that one. If we want to know how many maximum electrons there are, remember it's 2 times n squared, so that would be 2 times 3 squared, so that's going to be 18. Remember, we said that each orbital can hold 2 electrons. Okay, so we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so we've got 18 total electrons when n equals 3, and we have all of these orbitals filled up. Okay, we'll leave it there for this one, and we will continue in the next and hopefully last part of the Arrangement in Electron series. As always, thank you so much for learning with me today, and I will see you next time.